Okay, so welcome to lecture 7. This lecture is a continuation of our previous lecture where we introduced the notion of a derivative, right? Which we should probably recall a little bit about that, okay? So recall. So the derivative of f of x, or I'll just say f at x, which I should probably emphasize at the point x is defined by the following limit. So f prime at x is equal to the limit as the change in x goes to 0 of the difference quotient with the differences in x. Okay, sometimes you'll see delta h, doesn't matter, it's just a change. If we're perturbing x by a little bit, and we're looking at what happens as this value goes to 0. Now, this derivative is defined by this limit, which means that in order for the derivative to be well defined, this limit has to exist. Right? So I should probably say provided this limit exists. Right? Which will not always be the case. We're not going to worry about those cases just yet. We will at some point, but for now, most of the examples we'll look at, this will exist. Okay. Now, can anyone recall what the most important property of this is? Like, why are we concerned about the derivative? What does it tell us? It's the whole thing I was motivating it by last time. The slope of the tangent line at that point, right? So very important. So this is star, double star even, important to remember. The derivative, well, actually, I'll just use shorthand notation. So f prime of x, say maybe gives us the slope of the line tangent to the curve of f at the point x comma f of x. Okay, I can't emphasize that enough. That's why we care about it. There are other implications, there are other reasons why we would care about it. But to me, when I'm learning or teaching calculus, I think of that, right? So for example, if we're observing some curve like that, right? The graph of some smooth function f. And we want to know the slope of the tangent line at some point C, right there. Then the slope of that line, right there, the slope of that line is the derivative of f at C. So let's write that out. As slope f prime of C. Which means if we're standing right here at C, and we want to know how the function is behaving, we know that the slope here would be negative, which means if we increase a little bit to the right, we're going down the function, right? It's pointing down, so we go this way, we're down the function. We went to the left, we go up, right? Around that point C. So provided you have this notion like ingrained in you that that's what the derivative is telling you, it should be easy to figure out the derivative of something like this. So, so get like an example. Let f of x be equal to some k, where k is some real number. So it's just a constant function, right? So the graph of this function looks like what? So maybe like here's k, right? Then the graph of that thing looks like this. Right? This is the graph of a constant function. So if we understand that the derivative is the slope of the graph of the function at a point, right? No matter what value I pick in the domain, like if I pick this value right here, C, right? So what's the derivative of this function at C? What's the slope of the tangent line to the curve at that point? C comma f of C. It's 0, right? The slope everywhere is going to be 0, right? So we can conclude that in this case here, f prime of C is equal to 0. Just based off of understanding what the derivative is telling us, right, if it exists. So again, for those of you that have struggled in calculus, I want to re-emphasize this point, that conceptualizing what you're working with before you try to calculate anything is important, right? Yes, you could like use this formula to prove that this is true, but you don't have to if you understand the concept, right? Any tangent line to this graph is going to be flat, which has slope 0. Done. That must be true. Okay. And that's going to be the first rule that we encounter. We're going to slowly build up these rules throughout today's lecture. So one, we can say f of x equals to some constant implies that f prime of C is equal to 0 for all real number C. Okay. Now we can introduce Leibniz notation to kind of make this cleaner looking for now. So f prime was one way that I expressed notation for the derivative at a point, right, or the derivative of a function. But another way would be to write this: d dx of some constant k is equal to 0. That's kind of another way of applying the derivative to a function. So technically speaking, the derivative is what's called a linear operator that you can use to operate on functions in a linear way, which we don't know what that means, but that's technically what it is. So that's what this notation is emphasizing. It's an operator that we can apply to a function. Okay. Derivative with respect to x, d dx. But the constant function, there's no x in there, it's just a constant, which means it's flat. So any function of this form, you apply that operator, it's going to give you 0 back. Okay. So let's look at another simple one. In fact, before I do that, I'm going to go ahead and erase this notation and just use this, because this is what you'll see in your textbook. So the derivative with respect to x of any constant k equals 0. This is for all constants k. All right, so let's see if we can think about another simple type of function. So what about this function? Maybe I'll call it g this time. So g of x is equal to x. Okay, so hopefully all of you know what this is. It's a line passing through the origin, right? So it looks like this. One, two, so forth and so on. Okay. Now, this guy here, we can probably also reason about just like we did with the constant function, right? So I pick any c I want, like right here. That's going to be c right there as well. What's the slope of the tangent line here? It's the same as the slope of the line, obviously, right? Hopefully that's obvious. So what's the slope of the line? It's just 1, right? If you remember, or maybe recall, from college algebra or something like that, lines that form y is equal to mx plus b, right? Where this right here, that's your slope. And then this right here is your intercept. That equation look familiar? That's the equation of all lines. You can write them that way. Right? This is the slope-intercept one. So this is like a simplified version of that, right? It looks like this. Like this is really equal to 1 times x plus 0, right? And if we look at any line that's tangent to that line, it's going to have the same slope, right? So what do we conclude about the derivative at any point? This is g, I'm sorry. So g prime, like at that c, what's it going to be equal to? 1, right? It's the same as the slope of the line. And this is true no matter what c we plug in, right? For every real number c, it's going to be 1. Okay? So that, in a sense, gives us a function back, right? We plug in a value, we get out something. Same thing with the constant, actually, too. So the way that I'm going to write this is, so if we take the derivative with respect to x of x, it's just going to be equal to 1. However, I'm not too satisfied with this, being a mathematician. This seems too specific to me, right? Because, well, let's like look at another line and see what I mean. what about a function like, this is another example. We got h of x equals to 4x plus 1. So that more or less looks like this. So 1. It looks like this. Okay. Now, it's still just a line, right? So no matter where I pick my c to take the derivative at, and I go up to that point, so c comma f of c, and I look at the tangent line, it's like actually like right on top of it, but I don't want to ruin my marker. What's the slope of the tangent line at that point? 4, right? It's just 4. If that coefficient of x was a 10, what would the slope of the tangent line be? Just be 10, right? So it actually seems that, oh, maybe, and not maybe, exactly, the derivative of anything that looks like this is just m. It's just the slope of the original line, which would generalize this, right? This is like a specific case of that idea. So instead of writing that, I'm going to say the more general version. And m could be negative, it could be positive, it doesn't matter, right? And the intercept value, the b, doesn't do anything at all, right? That b doesn't change the slope of the function. It just raises it, right? It raises it up and down, right? The slope still stays the same, which makes me think, oh, this has to be true for any constant that you're raising the function by, right? Like, let's just consider another example, maybe f of x equals to like x squared plus 3 or something, right? Again, we all know what the parabola looks like, right? Y equals x squared. It looks like this. Okay. So this is just y equals x squared. That function there that I wrote is just that thing picked up, right? It's just, so that is, so 1, 2, 3, it looks like this. Right? So if we wanted to know, like at 2, for example, like what is f prime at 2? We don't know, right? We actually found that out last time. We calculated it last time. It's 4, right? We know this from last time. It's 4. Oh no, sorry. Okay, I should say this. So maybe I'll call this function something else. Like I'll call this like r, and I'll say x equals to x squared. So I know that f prime at 2 is 4. We did that last time. Okay. But again, if we think about it, what that is telling us is the slope of the tangent line at that point to that function, right? Now, does raising the graph of that function change the slope of that line? Like, are these going to be any different? Nope, they're not going to be different. All we did was raise the thing. We didn't change the curvature of it, right? So we can conclude that, what is it, r? So r prime of x must also be equal to 4, right? Because it's just this thing, which we know the derivative at 2, raised up, right? So this is not a rule that you would see in your textbook, but I'm trying to build up the rules. So maybe we can just make note of that somewhere, like maybe over here. So we note that the derivative with respect to x of f of x plus any number k is just equal to the derivative with respect to x of that function, right? Because when you raise it up and down, it doesn't do anything to the thing, right? Like conceptually, does that make sense? Right? We're just picking the original function up and down. You can subtract, add, whatever. But if the shape stays the same, nothing is going to change about the slope at a given point to the graph. Okay. Now, I'm just going to go ahead and write the next rule. The derivative with respect to x to the power n is equal to n times x to the power n minus 1. Okay, where n is just some rational number. Okay. So where does this come from? Well, without deriving it completely, recall that in the previous lecture, we showed that dx of x squared, we did show that this is equal to 2 times x, right? We did show that. First, we calculated for a single point, but then we just kind of generalized it by replacing the 2's with like an x and did all that algebra, and we concluded that, right? So this does indeed return a function of x. So the derivative as an operator applied to a function will sometimes return another function of x, which gives you the derivative at every point in the domain, okay, provided the derivative exists at those points. So that is a specific case of this formula here. Okay. So we should just probably apply it somehow, right? So let's look at an example. An example like problem. So find the slope of the tangent line to the curve of, say, y equals to x cubed minus 1 at x equals to 2. Okay. Now I'm going to pause the recording because I want you to kind of try this on your own and think about it. All right, so find the slope of the tangent line to the curve of this function at x equals to 2. All right. Now, I just wrote down this rule here, which this is also called the power rule. I should have said that earlier. So this is the power rule. There you go. I just heard the correct answer. It's 12. The reason for that, well, just kind of go through it. So notice that none of these rules really apply to this thing, right? Because it doesn't look like something to a power, and then there's like an extra bit, right? But what I was just trying to emphasize is that if you have a function and you're just like raising it or lowering it, and the shape of the curve doesn't change, then there's a relation between the curve before it was moved down or up and the curve that has been moved. So right here, this would be, this is the curve of x cubed, right? That's not the same curve. This thing has been shrunk down by 1, right? So that would look like this. Right? Now, looking at the green one, looking at the black one, if I want to know, so like, let's see, this is kind of off, but like, if I want to know the slope of the tangent line, like right there, right? That's the same as the slope of the tangent line right there, right? So one way of solving this problem is to find the slope of x cubed at x equals to 2. Doing that's equivalent to finding the slope of this thing at x equals to 2, because the shape has not changed when we brought it down. So, like, okay, let's just talk about it. What's the solution? So dx of x cubed is equal to, by the power rule, 3 times x squared, right? This will give us the derivative of that function at any point, right? And this will have the same slope at a point, at a value of x that this one will, right? So then we can say 3 times 2 squared is equal to 3 times 4, which is equal to 12. Again, I'm trying to emphasize that just because we took the green thing and brought it down doesn't mean the slope is going to change at a given x. That's what I was trying to emphasize with this example. So we use that idea together with this new power rule to find the slope. For example, like it might look like that, whatever. In fact, it's probably like way up here, but it's 12. The slope is pretty steep. Okay. Was that too confusing, or does that make sense? Okay. So again, I'm trying to emphasize the ideas rather than the computation. Like, yes, you're going to have to compute things, but the idea is the behavior of this curve is no different than the behavior of that curve in shape, right? They have this exact same shape. So if you can find the derivatives of that thing, then you know the derivatives of that thing, because the shape is what gives us the value of the derivative, right? So hopefully that makes sense. Okay. Now, maybe like, because I've kind of like really tried to emphasize it, you realize that adding or subtracting a constant doesn't change anything about the shape of the curve, right? All right. But what about if we somehow like multiply the values of x, right? Multiplying the variables will do things to the shape of the curve, right? You've often probably heard the term scalar multiple. What that is implying is that you're scaling the function. You're either making it increase faster or you're slowing it down as you increase x. So for example, let's start very simple with a scalar multiple of like that. Or maybe that to make it a little bit easier, because we already did this, right? If it's just a linear function, then we're scaling by m, and that's just the slope of the line, right? Let's make it a little bit different with a quadratic term instead. So what does this look like? Well, is this like, okay, I'll draw roughly the best I can. So this is like just x squared is that curve right there. Now, scaling it by 2, what's going to happen as I draw this way? Right, like, is it going to go faster up on both sides, or is it going to slow down in growth? And by growth, I mean the y values. It's speeding it up, right? We're increasing the rate of growth by 2, right? So like when the scaling is horrible in this picture, but like here's 1, right? That'll be 1 squared is just 1, so on just x squared it'd be right there, right? But on that one, at x equals to 1, where are we going to be at? Up here. At a half, we'll be at 1. And it's symmetric about the y-axis. So that thing looks like this. See that? As you increase x, it's growing faster, right? It's growing twice as fast. And maybe you haven't thought about scalar multiples in that way before, but that's what it's doing. It's scaling the original function and making it either grow faster or grow slower. For example, if I wanted that thing to grow slower, I'd scale it by half, and it would grow half as fast. And it'd be fatter, right? If I was scaling it by half. Scaling it by 2 makes it grow faster, so it's skinny. If I wanted to really speed it up, I'd multiply by 100, and then it's growing 100 times as fast as this one, right? So if it's growing, in this example, twice as fast, okay, twice as fast. And like, if I look at the original function x squared, now look at the slope of the tangent line right there, right? This is the original x squared function, right? What is, like, when we think of growth, what do we mean when we say growth, right? Or rate of growth? Maybe we mentioned last time average velocity, right? So one way of measuring rate of growth is with, I'll just go ahead and write it out. It's your change in y over your change in x, right? Change in y over change in x. Change in y over change in x, right? That's like your rate of growth. For every unit that you go this way, we change in the y direction this much. Right? Change x this much, change y that much. How much you're changing that versus that, okay? Now, if we think back to this scalar multiple, it's growing twice as fast, right? So, you know what this actually, what this looks like, right? Change in y over change in x, it looks like this. Hopefully the camera can still, I'll write it over here so the camera can pick it up. remember how we derived the definition of the derivative? Change in y over change in x, right? That's how we derived it. That's how we got, we took a limit and got the slope of the changing line at a given point, right? So if the rate of change or rate of growth is literally that ratio, right? And that thing is growing twice as fast as this one, can we guess what the derivative of 2x squared is in relation to x squared? It's twice. It's growing twice as fast. The rate of change is twice as much as the original one. And whenever I say original, I mean this x squared guy, right? That's growing twice as fast as that. So the rate of growth, which is the derivative, as you take the distance to be very, very small, right? The derivative is going to be twice as much as this one, which leads us to the next rule. Does that make sense? Derivative is changing y over change in x. If your change in y is twice as much as your original function, then it's going to be twice. The derivative is going to reflect that, right? So the fourth rule is that the derivative with respect to x of any constant times f of x is equal to the constant times the derivative. Again, I know it's so hard at first to really like get into this mindset of like, well, honestly, most of you probably haven't been taught mathematics in a way that is about this type of thinking, like imagining, oh, it's getting two times as fast. It's imagining the thing, right? That actually, once you get into that rhythm, it makes mathematics more enjoyable and not such like a tedious pain in the ass, right? Instead of thinking about calculating things, literally like try to just stop, right? And throughout the semester, I'm going to try my best to help you get into that mindset, right? So let's look at an example. Find the derivative of y equals to 3x to the power 1/2 plus 4. And I'm going to pause the video again so we can think about it. Okay, so let's find the derivative of this function. It will be another function, so it will be a function of x. And by the way, it will probably not appear this way in your examples, right? 1/2 x to the power 1/2, it'll probably appear like this. And you'll have to know that the square root is the same thing as the power of 1/2. Okay. All right. So solution. Well, we have a constant multiple times this thing, right? Constants we know that we can just take out, right? Put them in front of applying the derivative operator. And then we have a constant that's raising up or down the function, which those don't do anything to the slope of the function. So really, we should focus in on the derivative of square root of x, which is this guy, right? And then scale it by 3, right? So I'm going to write it the way that it will appear as a solution in your textbook first, and then I'll kind of describe how I would think about it a little bit differently. So the solution in the textbook might look like this. So dy dx. So So this is the derivative of y with respect to x. So that means we're going to apply the derivative operator on both sides of that equation. Like that. Now, I mentioned earlier that the derivative formally is something called a linear operator. We're not going to talk about like the exact details of that, but basically this operator, taking the derivative on a function, will distribute across sums and differences. So we can think of this as the following. We're going to write this formally as a rule in a moment, but let me write the solution first. Okay, so when I say linear operator, I mean that it's an operation you can apply to functions and it distributes across sums and differences. So it just got distributed in. Is that clear? Like a linear operator. It's an operation you can throw onto a function and it does stuff. Okay, and the linear part means it's kind of more or less distributes across sums and differences. So as before, like we know the 4 didn't do anything, right? And then if we look back to our very first rule, what's the derivative of a constant? It's just 0. So that right-hand piece, this is nothing, as we would expect, right? But instead of using that rule blindly, I tried to emphasize the point that it's trying to make. Lifting and raising a function doesn't do anything to its shape. So it shouldn't do anything to the rate of change or the slopes or the tangent lines. Right? So that goes away and we just left with this. Now, this part, we can apply this rule, which again, I tried to emphasize that we are doing what? We are scaling the rate of increase of that function, rate of change of that function. In this case, we're scaling it by 3. So we can just take the 3 out. Like that. Now we're basically there, right? Provided we can figure out that derivative, we're done. Okay. Well, to figure out the derivative of x to the power 1/2, we apply the power rule. Okay. So what does this become? Well, if I was trying to be, I would write more right here, right? If I was in your shoes and I had a big piece of paper, I'd fit it right there. Now, because I don't, I'm going to split it up, and maybe this might be useful for you guys to do as well. Because as the semester goes on, we're going to encounter equations that get longer and longer and longer, and it's a mess. Sometimes it helps to pause, let's figure this out, and then come back to this equation. So like maybe in my solution, I'll be like over here or something, and I'll say like, okay, the x of that piece that I'm concerned with, well, I apply the power rule and I get 1/2 times x to the power 1/2 minus 1. I just literally that. Okay. So then, what does this become? 1/2 minus 1 is what? Negative 1/2. Anytime you have a negative exponent, you can do what? You can write the reciprocal of it, correct? Like just, this is from college algebra, like just remember that, where am I going to put it? Like here maybe? Like x to the power negative a is equal to 1 over x to the power a, right? When you have negative exponents, typically, especially if you're like entering them into a textbook homework type of thing, you're not going to leave the negative exponent as it is. You're going to rewrite it in the reciprocal form. So this will be equal to 1 over 2 times root x. You see that? Or did I jump ahead too far? I don't like the way you're looking at me right now, or looking at that in particular. I'll write one more line. This is the same thing as 1/2 times 1 over x to the power 1/2. Right? That's the same thing. X to the power 1/2 is just root x. And these are multiplying each other, so numerator times numerator, denominator times denominator. Please, if there's ever a point when I'm writing algebra, like, and it's not computing for you, tell me, because it's probably doing the same thing for other people. And I know a lot of you, or at least like when I was in your shoes, I was embarrassed about a lot of things involving fractions. I was just embarrassed. I didn't want to say anything.
So restated 1/2 exponent equals the square root of 8.
Yes, square root is another way of writing. So like that's another thing that important to remember, that you can write fractional exponents as radicals. Okay. But yeah, so if I reduce everything down, eventually I get this. And like, honestly, I remember when I was taking calculus, and I was like trying to submit homework on like whatever web thing it was, and it just wasn't working. I had the right answer, it just wasn't in the form they wanted. And that's probably like one of the most frustrating things that you'll ever encounter with this type of course. So that's what that becomes. Now we can substitute it in. So what do we end up with? 3 times that. Or just 3/2 square root of x. Yeah. That's the derivative of that guy right there. Yeah.
I thought that the derivative of x is separate.
What do you mean by that question?
You
curious.
see how on top you have k times the derivative of x.
Yeah.
Equal to fx.
Oh yeah. This is equal to the constant times the derivative.
So we move the constant to the side.
Yeah, I moved it out correctly. That's right there. I'm moving the 3 out.
I get rid of the derivative of x.
So I didn't. It's still there. This thing, I just calculated it because I was running out of room separately, right? Once I figured out what it was, I just replaced this whole thing by what it was. That. Like these are the exact same things. Like this right there is precisely this right there. And I just substituted that in for that and I get that. And you know, it's just multiplying it out. Okay, so question, any more questions on that? Okay, again, sometimes it might help to do that I was forced to do. You're gonna have a bunch of stuff in little chunks in your notes, calculate the things that are easy, and then plug them back in. And just be very careful that you're meticulous about it. Okay, so that's the solution. We have one more rule. Actually, technically 1, 2, 3 more rules. But the others should just follow quickly. Actually, I don't need to write it. I'll write it right here. Derivative with respect to x. Again, I'm calling this an operator because we can take this and apply it to a function, right? So let's assume that these functions are differentiable for all x. that limit thing exists, right? And we want to know the derivative of the sum of these two functions. Can you guess what that is going to be? Like, there's going to be like something right there. Right, so it's going to be the derivative of f plus the derivative of g. Another way of saying that is the derivative of the sum is the sum of derivatives. Okay. But before we use it, we should probably reason why this would make sense. Now I know I've been calling it a linear operator. I can't help myself because grad school just made me think that way. But when these linear operators, we know, I mentioned earlier, they distribute across sums. So like already you could have guessed it, okay? But why does it make sense in this case? Well, what is the derivative measuring? It's measuring the change in y, right, over the change in x, okay? The only thing that if you're looking at the sum of two functions, right, and you're looking at the change, like that is a single function. The change in x is the same, right? Like we just take small changes in x, whatever. But the changes in y depend on these two things, right? Now imagine that wasn't there, right? And we just take the derivative of that. The change in y only depends on this as we look at changes in x, right? Now, if we add another function to it, g in this case, isn't the change of this sum dependent now on both of them, right? Like how fast is that changing and how fast is that changing together now, right? Their cumulative change in y is now going to be the change in y for the sum function, right? Like if you like kind of broke it up into two pieces, like with like f of x was x squared and g of x is equal to x, right? And you didn't plot them as one function. You just looked at them separately. Here's the change for g. Here's the change. I mean, the graph of g and the graph of f, right? And as we're like looking at changes in x, like here, right? Changes of x here. And we're looking at the sum of them, which will be something like a really fat one, like that. That's like the sum of those two things, right? Maybe it's, yeah, we're scaling it. No, we're not scaling it. I should definitely not say that. It's somehow like going faster. And it's like steeper too. Okay. So looking at the sum function, like the rate of change, it depends on the rate of change of this one and the rate of change of that one. Together, that's what's influencing that thing, right? So that's kind of why this would make sense. Now we could derive it, and actually in your textbook, there is a simple derivation of the reason why this is true. But the idea is that both those things are contributing to, in a sum, how this is changing. And the same can be said for subtraction. Right? Same exact thing. So if we look at an example like find dy dx for y is equal to 2x cubed plus x squared. Like what's the answer right away? Just using the power rule and using that sum rule.
6x squared plus 2x.
Yep, that's it. Now, if you wanted to see the full solution for your notes and how you should definitely write your solution if you're like writing it on a written exam or something, it would say, so like right there, it'd be, well, dy dx. That's my y, so I'm applying this derivative operator on this sum. I'm applying it to the sum. And then I can use this sum rule, which we justified by saying that the rate of change of this is dependent on the rate of change there and the rate of change there. So then we can split it up. Like that. That's applying the sum rule. And then I see a constant that I can take out, because the constant is just scaling the rate of growth for that x cubed guy. And then we apply the power rule. So this will be equal to 2 times 3x to the power of 2. Find the power rule there. Plus 2 times x. And finally, this simplifies to 6x squared. That's 2x. Okay. And I think I'm just going to write the next two rules. And we'll discuss them when we encounter them next time. So I'm leaving the discussion out for these next two rules. My leg is killing me. I'm tired of standing. So derivatives of the two most basic trig functions. The derivative of sine x is cosine x. That should look very surprising. And then the derivative of cosine x is negative sine x. So those are derivatives of the basic trig functions. Yeah.
I had a question for you. So I thought f of x meant y and g of x meant different y. So why is it the solution for the problem example you put them together at the same function?
They can mean whatever, right? Like you can treat them in an abstract way, right? So when I looked at, like, for example, the problem that I raised, right? I looked at this and I said, oh, I can let that be f of x. And I can let this one be g of x. If I let the f of x be that and g of x be that, if I say that's what they denote, then it looks exactly like this equation here. So then I can use that equation, right? It just depends on how you choose the notation that you have, or like how you use the notation, right? And we'll discuss this more when we get to some more rules. In fact, substituting in like these pieces of equations with labels is something that we will encounter again. Okay, so I think that'll be it for this recording.